What non-engineers need to know about structural masonry. We have our program description here, along with our learning objectives. We have continuing education credits for MISL professional development hours and AIA continuing. We have our provider statement as required. In today's giveaways, we have a street design of masonry book by Dr. Bennett, and we have a code master. You'll see a little plastic box coming around your way. You'll put your name or business card in there. We will give that away at the end of the session. Today's sponsor is Best Block, and we have Mark Wilhelms here, if you'd like to say a few words. Best Block offers products in a wide array of shapes, sizes, colors, textures, and finishes. Best Block delivers strength, beauty, and function to any residential or commercial project. Their team is very successful and very professional and ready to assist you. Mark, do you have a few words?
Yeah, thanks, Margie. So, Midwest Block, Best Block, we're just going through that naming transition. The same people, same company. I started my 29th year selling masonry, so enjoy doing it. A couple quick announcements. One, just thanks for coming today. It's a great program. Had Beth put on this program multiple times for us over the years, and she gives a great perspective how to reduce costs of building. And it's a good program. I know you'll get something out of it. And second, on the announcement, as you leave today, Diana Johnson's going to be at the back table. Diana, can you raise your hand? Does anybody here know Diana Johnson? She's only been selling masonry for 27 years, 24 years, 26 years. She's retiring. Tomorrow's her last day. So you can. And she's unloading all her stuff on me. But no, Diana, we've loved the relationships you've developed with everyone, the professionalism, your knowledge that you've shared, and you will be missed. But you are always welcome to come back to the Wednesday architectural series at the Masonry Institute. So we hope we hope you'll be here and you can help maybe be a ceremonial marching. So, but thanks. And so, Beth, are you going to do the intro?
I am going to do the intro.
So you can do it, but this is Beth. She's great.
Thank you, Mark. Thank you, Best Block. Diana, congratulations. All the best to you. So let's get to today's speaker. Beth Suminski, she's a PESE for FORSE Consulting. She's worked for 25 years as a structural engineer in the fields of consulting, engineering, software, and continuing education. During her first few years, her experiences in construction, litigation cemented her understanding of how and how not to design a structure. She spent the following years as a practicing consulting engineer in San Diego. In her current position with FORSE Consulting, she continues to pursue both the design and educational aspects of structural engineering. One topic Beth highlights is structural masonry design in partnership with IMI. And Beth is a licensed PE and SE in California and licensed in PE in Arkansas. So please give a warm welcome for Beth Suminski.
Thank you. Thank you, Margie. And I want to double check that you can hear me. Is this a good volume or do I need to speak up? Good? Oh, speak up. All right, I'm actually going to try to move this a little closer. Let's see if that will help any. And I will talk louder. So, the topic today is what non-engineers need to know about structural masonry. Now, I am an engineer, so I will try to convey this information in a way that's not dry and boring, but sometimes it can be. We have a lot of numbers, but we also have a lot of pictures and things to get through that will help us understand this concept better. So the reason that we created this presentation is because we think there's a huge misconception in a large percentage of design professionals today that masonry is not a competitive building material. They think that it's too archaic or too costly or too limited, and that misconception could not be farther from the truth. Masonry today is more cutting edge, more efficient, and more flexible than we give it credit for. So we've already gone over my background. I worked as a consulting engineer in Southern California for a while, and then I moved to a national structural engineering software firm, and then for the last 8 years I've been with FORSE Consulting, and FORSE teams up with IMI, the International Masonry Institute, to promote masonry design.
We try to put that up just a little bit, the microphone, the other one. We clicked on the other side.
Is that better? No?
Is that better?
Okay. All right, yeah, now I can hear myself too. Okay, so our learning objectives today will be to first review structural masonry basics. We know that it is efficient and economical, and we're just going to go over that. We're going to discover some updated design criteria and design methods for masonry. We will learn tips for designing economical masonry walls, and we will explore some structural masonry details to find the ones that help us out the most when it comes to construction. So the fact that I began my career in Southern California greatly impacted how I perceive masonry design. In San Diego, which is where I was based, we used masonry for a multitude of structures. There's a big military presence there, so we used it for a lot of barracks. We used it for park restrooms, which we called comfort stations. We used it for gymnasiums, which is a picture that you see on the top there. We also had we had seismic requirements and blast requirements because of that military presence. And masonry handled it all. We used high strength, heavily reinforced, specially inspected masonry, and it never occurred to me that it could not handle all of these things that we were throwing at it. But then I moved east. I currently live in Arkansas, and it came as something of a surprise that people here don't use masonry to its full potential. So again, that's why I am speaking on this today, is just to educate people on how we can utilize masonry to its full benefit. So this is the order that we will address our topics today. We'll start with those masonry basics, and we will move into a masonry systems overview, take a look at stair towers and shaft walls, interior partitions, the masonry and steel interface, and then we'll wrap it up with some information about lintels, and we'll also touch a little bit on control joints. That somehow got left off here. So we'll start with these masonry basics. And when we talk about spotting a good or a bad masonry design, a lot of that is tied into cost. So much of the masonry design today is inefficient. It has some inherent design assumptions that have been made about it, or it has been reused from a previous project that was poorly designed. And if we keep reusing that bad design, that leads to that continued inflated cost estimate. And the key items that are wrong is that engineers are using the wrong strength. I can say that because I'm an engineer and I have done that. It may be harder for you to go to your engineer and say you're using the wrong design strength, but we're trying to get that message out there. And if you see 1,500, which is a number we'll talk about later, hopefully that triggers you to say, wait, that's too low. We're not using the capacity of masonry that's already in the project. We're adding reinforcement to walls that don't need it, especially in partition walls. And we're making a poor choice of material for lintels. So moving away from that bad design to a good design, we're going to be moving away from inefficiency and more cost, and we're going to be more efficient with less cost. And these are the things that we want to watch out for, moving away from that strength of 1,500 to something higher, 2,000 to 3,000 range. Control joints, we want to move those away from opening edges and space them out in our structure. Steel lintels, it is the default in a lot of masonry projects, and I don't know why. We should move away from that and looking at masonry as our default lintel material. We need to move away from reinforcing all partition walls and going towards, most of them do not require reinforcement. And then again, there is a belief out there that masonry is not strong enough to take load, that it needs to be non-load bearing, and we want to move towards utilizing all the masonry and loading it up as much as we can. So structural masonry can be used for bearing walls, partition walls, shear walls, firewalls, shaft walls, basement and frost walls. It can be used all over your project. And it's a finished trade, so it has those nice tight tolerances. You don't have to cover it up in the field. There is very little or no lead time for production, review, and approval of shop drawings. And because of that, it adapts easily to field changes. We had a quote that with a masonry project, if you need to make a change, you can just pick up the phone, get it approved, and then the change can be done. There's no waiting around for reissuing shop drawings and getting those approved. So this is one material, and it can be used efficiently for all these aspects of your project. And it's likely that masonry is already on the job in some form or another, so we need to utilize it structurally. It's also very sustainable. That's a big buzzword right now, and the fact that a lot of the block is locally produced also means local employment, which helps your local economy. So we're going to start with taking a look at masonry through history. This project is the Monadnock building in Chicago. It was built in 1892, well over 100 years old. It is 16 stories tall. And at the time, it was the largest load-bearing brick building constructed. It's not CMU, it is brick, but it's still a masonry product. So at that time and at that height, that meant that the walls at the base were 6 feet thick. So it's maybe not the most efficient structure to build today, but really what I'm trying to highlight here is that we've been doing load-bearing high masonry for a long time. In the past, a lot of the masonry was built based on an empirical design methodology, which meant tables. This worked before, we're going to tabulate it, and then we can just pick from this going forward. So even in empirical design times, though, this table here has Chicago underlined, and it shows that we could easily go up to 8 stories at that time, and we can, of course, go higher today. And the reason that we can go higher now is that we started doing more testing and more engineering and developing methodology for designing walls, not just relying on what worked in the past. So the timeline here, I'm not going to step through every date there, but our first engineered masonry code was in the 60s. And since then, we've also started to do more testing, and software has been developed. And that has really brought us into a new era of masonry design. So in 2009, masonry whole building software was released, and FORSE has been utilizing that software, and now it's been 15 years even since that, so things have come a lot farther. So the point with this is that we need to move away from these old empirical methods of design and get into engineered design to take the full advantage of masonry. And just as a guide as to how tall masonry can go if it's properly engineered, this is a slide where for an 8-inch CMU wall, this is in seismic design category A, so we're not really looking at seismic, we're just looking at wind loads on this. But an 8-inch wall can easily go 24 feet high with light reinforcement. And by light, we mean rebar and grouting at 4 feet, 48 inches on center. If you bump that up to a 12-inch block wall, you can easily go up to 32 feet with that same light reinforcement. Now, if you want to get a little bit heavier, we're going to look at the next tier of reinforcing, which would be 2 feet on center. You could go up to 36 feet high with that 8-inch CMU, and possibly even 52 feet high with the 12-inch CMU. And that is what you see in the picture here. This was a high school in Wisconsin, and the top of that gymnasium wall was 51'4", and that was done with the 12-inch block with the 24-inch on-center reinforcing. So masonry is a system, and when we're talking about the strength of it, there are a few parts that come into play there. Just like every engineer likes to make the joke, there's no such thing as cement, it's concrete, because cement is just part of the system. That's similar to masonry. The block is a huge part of the system. That is the building block of what the strength is made up of. But there are additional components as well. There's the mortar, which binds it all together. There is vertical rebar. This is for strengthening the wall, typically for out-of-plane wind or seismic loads. And then there is often horizontal joint reinforcement. And this could be mainly for crack control, not so much a structural item. And then, of course, there is the grout that binds and glues it all together. So this system has a design strength. And it's this number that we want to start increasing in the engineering and just in the construction field in general. So these building blocks are all able to be put together on site in a very simple manner. You can do small, one-story, lots of wall structures very simply, but also you can do more complicated multi-story structures with openings and masonry lintels as well. And because you are building this on site, it's very easy and straightforward to do. So a little bit more about the strength of your block. For sustainable masonry design, you want to utilize the strength of the block that you're actually getting. So this is what we're calling the locally available block strength. All block that's produced is then tested to find out how strong it is. And this slide in your handouts is going to have a few things that fly in and out here. So it may not be as obvious once everything is complete what I'm trying to say. But this is an old table. So these were the design values for an old code. The block strength was the 1900, and then the overall masonry strength was the 1500 PSI. And I've been a structural engineer for 25 years, and when I first started, that was the value that we had on our drawings. 1500 was the minimum, so structural engineers are very conservative, so we always just designed to the minimum and said, okay, if we get more, great, we know we're covered, but that number has now just been burned into the consciousness of engineers for decades. And it's very hard to eliminate that number. Now, once your block strength goes higher, then your overall system gets higher as well. But we don't want to look at that first row anymore. That 1500 is gone. It's not even in the code anymore. So when new values were added and more testing had been done, they found that with a minimum 2,000 block strength, you also get a minimum 2,000 overall strength. So that 2,000 is now the minimum in the code. So 1,500 is not even in the code anymore, but I still see engineers designing to that value. So 2,000 should be the bare minimum. Now, for the next level of strength, which is the 2,500, the testing in the new code found that the block only had to be 3250 PSI. I don't want to throw a lot of numbers at you, but it actually found that that level of block, which was not as high as previously thought, would achieve the same strength. And the reason that it's highlighted in yellow there is that the testing data on most of the block that you get is going to exceed that value. So what you're actually getting in the field is probably going to be at least this 2,500 PSI overall strength, which is a whole 1,000 PSI higher than what a lot of engineers are designing to. And then it's also easy to obtain that last value. A lot of the block that we see also comes in above that 4,500 PSI strength. So if there's one thing that we harp on a lot at FORSE and with IMI, it's F''M. This is the strength of your masonry, and we would like it to be about 2,500, but at a bare minimum, 2,000 needs to be what's used. And it's important because everything becomes more efficient with that higher strength. Your bearing walls, non-bearing walls, shear walls, all of those can resist more load. Your lintels can span farther. Your columns can take more load. Any rebar that's lapped within it makes that lap length shorter. Any connection that's connected into it is much more efficient as well. So it all trickles down from that strength of your masonry. We did a few cost studies. So this specific one that we did was a 4-story dorm. And initially, it was designed with that F''M of 1,500, and it yielded a requirement for 12-inch block. So we came in and we said, what if we use what's actually probably on site, which is 2,500? And what we found was that the upper stories could utilize an 8-inch block and the lower stories could utilize a 10-inch block. And that resulted in an 18% savings on the installed masonry cost. So for a $2 million masonry contract, that was $360,000 in savings. This study was done a long time ago, so these construction numbers have probably skyrocketed since then. We also looked at an 8-story load-bearing dorm. And so for this one, they did utilize the F''M of 2,000 minimum, So at the upper stories, they found that using this strength, they could get away with 8-inch block. But at the lower levels, then they had to go thicker. And that was not architecturally desirable because you want the same floor plan. It's a dorm. Everything stacks from above to below, and you don't want that reduced footprint at the lowest level. So what we were able to do is to say, let's look at just specifying a higher design strength for those lower levels. And once we did that and bumped that up to 3,000, then we were able to keep that 8-inch block all the way down. So we talked briefly about one code that had been updated. There's another code that came into IBC 2015, and depending on where you live and where it was adopted, I'm not sure when it was adopted here in Missouri, but once the IBC 2015 was adopted, it also incorporated ICC 500, which is a requirement for tornado storm shelters. And it mandates those storm shelters for certain geographic areas and certain building uses, critical facilities, grade E occupancies, which would include schools. And the reason why this is significant is that Missouri has the highest wind speed required by this ICC 500 storm shelter requirement. We're in Tornado Alley. I live in Arkansas. It's just part of life. So that dark blue area represents that highest wind speed required. So if you are designing a storm shelter in this area, you are required to look at wind speeds of 250 miles per hour. And there are other requirements that go along with that for tornado debris. So anything that's picked up and then thrown at your structure has to be resisted as well. So if you are required to comply with this, your light frame structure is not going to be able to withstand those values. If you have wood stud or even cold form steel, you're probably going to be looking at a separate assembly that is masonry or something that can withstand those forces. So that's another good reason why masonry is an excellent building choice, especially in this region for those types of facilities. So the next image is some testing that was done. And this was to illustrate how masonry can resist this windborne debris that is generated during a tornado. So this particular specimen was a CMU wall, and then it had some veneer in the front. So we were really looking at whether or not that CMU could resist this tornado debris. This is the cannon that they fired a 2x4 from, and that 2x4 was traveling at 100 miles per hour for this test. So the video should play in a second. It starts out with it at full speed, and then it slows it down a little so you can see the impact a little more clearly. I hope it plays. We were having some trouble with it a little while ago. So I don't want to look at the veneer. That part is just for looks, but I want us to look at the wall behind it and how it didn't even budge. And that particular wall wasn't even fully grouted, but yet it still resisted the forces from that windborne debris from the tornado. So it's definitely something to think about when you're looking at your material choice for these schools or other areas that require that type of shelter. Are there any questions so far? I was going really quickly because I didn't want to lose anything, and now I think maybe I'm rushing a little. Nope. Okay. So our next section is a masonry systems overview, and this is really going to highlight how masonry fits into any type of construction that can come into play. It was brought to my attention earlier that some of these boxes have 1 or 2 or 3 check marks. There's no real rhyme or reason behind it. Anywhere that you see a check mark, masonry is a good choice in that system. So even in our light frame buildings like wood or cold form steel, masonry can still be utilized for stem walls, basement walls, shaft walls, interior bearing walls. We wouldn't really use them as, I'm sorry, that's exterior bearing walls. Well, it does say interior also, but we wouldn't really use them on the second story of a wood frame structure with no support below. So that's why they're not checked there. But then for any other material type, steel or concrete or precast, there is room for masonry, and there often is masonry utilized in your structure. One of the most common locations is at a stair tower or a shaft wall. And this is where I like to do a little pop quiz. So if you have the wall on the left, which is more lightly loaded, or the wall on the right, which is more heavily loaded, which of these walls will require more reinforcement? And it's not super intuitive, but if you think of building a stack of blocks, like I have a son and he likes to build up towers with his stack of blocks. You build up a stack of blocks and you go to knock it over from the side, it's very easy to knock over. But if you build up that stack of blocks and then you put your hand on top of it and push down, and now he comes along and tries to knock it over from the side, it's harder to do that. And the point is that when you load a masonry wall, you actually increase its resistance to these lateral or out of plane forces. So if you have a wall in your system, you would want to load it, and that actually can help bring down any reinforcement required in the wall for these out of plane loads. So the answer to that question was that the starred one, the one with the lighter load, would require more reinforcement. Again, not always intuitive, but definitely the case when it comes to loading these masonry walls. So the next few images are examples of how walls are incorporated into other material systems. This first picture, you can see those masonry walls are very robust. They have gone up quickly. Now we're waiting for the steel to catch up. And you can see that those steel frames are very small looking in comparison to the wall. Those are moment frames, or rigid frames, as some engineers call them. And when an engineer is designing the structure, they often make the choice, which material am I relying on for my lateral load, for my wind or seismic load? And oftentimes the masonry is ignored. And in this case, they were utilizing steel moment frames to resist the load. But the building doesn't know that the engineer ignored the masonry, and those walls are still going to resist any wind or seismic that comes along. Actually, they will probably be resisting that load long before those steel frames even get engaged. So I did not design this structure, and I'm not entirely sure what the thought process was there, but in my opinion, those steel frames probably could have been eliminated and just gone with the masonry. But it's just a mindset that sometimes the masonry is just overlooked for these lateral systems. This next building is wood framed, and you have another stair tower in the center there. So again, this should not be ignored. You can tie back to that. You can resist your lateral forces with that. You could also resist any gravity forces that you could tie into that wall. It plays nice with all systems. Another example here is of a structure that's going to be concrete. So you see the masonry towers going up there as well, and they will be incorporated into that system. Okay, so next section is interior partitions. And interior partitions are one area where we could significantly improve our standards and yield more efficient designs. Again, as an engineer who's been around for a little while, I remember schedules on our structural drawings, and it said for interior partition walls, you need reinforcement at 48 inches on center, and this was sort of the starting level of the project. Yes, there are locations where minimum steel at 48 inches on center is required, but it's definitely not everywhere. And we don't want to just be reusing these tables that are not necessary when we're looking at, everyone nowadays is looking to save money at every turn. So if we had this interior partition, and the code says that if it by definition is an interior partition, then it is not allowed to take any load. So the engineer will design the top and bottom so that it is not taking any gravity or lateral load. Really, the only load that it's seeing is from its own self if the building shakes and then you have a little bit of seismic force on the wall. But we still see this 48-inch on center reinforcement pretty common. But we don't need that. We can take out the bond beam in most instances. We can take out that vertical reinforcing in most instances, and our wall will still be able to support itself and the minimum loads that the code requires. These are some tables that we created to showcase exactly when you would need reinforcement in a wall of a certain height in a certain seismic design category. So the first one here is for seismic design category A or B, so very low seismic activity. These are interior partition walls, so they don't see the wind from the outside either. And what you'll see here is that for every block thickness up to 14 feet tall, you do not require any vertical reinforcement. So it's only as you get higher in a thinner wall that you require some reinforcement. But you see that starts at 96 inches or 8 feet on center, and then it slowly steps down or up, depending on how you want to look at it. So if you're in an area where you do not have high seismic activity, then this should be the default standard table in the structural drawings. And that alone is going to save you from all of the additional reinforcement and grouting that sometimes gets called out. Now, as you move up into higher seismic design categories, this is seismic design category C. There is a minimum vertical reinforcement requirement, but it is at 10 feet on center, not the 4 feet on center that we often see specified in the schedules. So again, that 10 feet on center is going to cover the minimum requirement, and it's really not until you get up into those higher and thinner walls that you need actual strength reinforcement. And that's where you'll see in the gray that that starts coming into play. It is not until seismic design category D that we have that 4 foot on center minimum requirement. So at this point, yes, we have now caught up to our old schedules, but if you have been building in an area that did not require this, then there has been a lot of wasted reinforcement going into those interior partition walls. I don't have a slide for seismic design category E or F, which of course the code does go on up to that. At that point, you're looking at specially reinforced shear walls, and there are additional requirements for minimum reinforcement in each cell, but again, those are sort of a specialized case for that seismic design category E or F. If you are an architect and you're trying to figure out what is the thickness of interior partition that I can have in my structure without reinforcement, or if you are just double checking something that you want to see if it requires reinforcement, IMI does have a software on their website where you can go in and plug in your wall height and then your region of the country, and then you would be able to check whether or not that interior partition reinforcement is required. We're not suggesting that you don't have your walls engineered eventually, but this is a good starting point and it's available on their website. All right, so now we're going to move into masonry and steel interfaces. We'll start off with a picture of what we don't want you to do. We don't want you to have steel lintels as your default. I like to think this guy is sitting there scratching his head going, how am I going to make this work? So you have this big steel beam as a lintel, and now they have to try to cover it up to make it look like the rest of the structure. And we see that a lot. Going back to these repeated uses of schedules from old projects, I also remember we had a lintel schedule for masonry structures, and it said for up to 3 feet, use a W8 by 10 or whatever the beam size was. Up to 6 feet, use this size of beam. And again, it was something that had been calculated to the worst case, and it was just reused, and that's the way it had always been done. So it gets trickled down to the rest of the structures from there on, and we're trying to stop that from happening. So where the steel attaches to the masonry can be a weak spot, and then you're trying to cover up. You have to make sure that fits in there. We're going to talk a little bit more about how if we utilize masonry for our lintels, then we would eliminate a lot of these potential obstacles. So here's another example. This one even has a, looks like a support on the other side of the wall, probably for the veneer coming out. And it's difficult to place. That ledge for the brick is also going to induce torsion in this beam, and you're just trying to cover the steel that you probably didn't need in the first place with those flimsy little panels on the side. The other thing we find is that engineers think that we need steel columns located periodically within the structure. I can't tell you how many sets of plans we've looked at where they basically designed the entire building as steel and then they wrap it with masonry. And it just doesn't make sense because the masonry can take that load. You don't need those steel columns in there. So this is an example where a steel column was designed and it was supposed to go inside the wall. But as you can see there, it didn't fit. It couldn't be covered up with soaps. So what they did is they bumped out around it. So now you've created this kind of unsightly bulge in the wall. You probably didn't need that column there for strength in the first place, so now you've added cost to the structure and you've lost some of your aesthetic as well. Even if you could fit your steel column inside the block wall, which they've done here, you're probably going to experience some cracking down the road. Steel is a different material than block. It expands and contracts at a different rate, and if that block contracts and that steel expands, then you're probably going to end up with some kind of cracking at that location. Another case study that we looked at a few years ago was for a retail structure, and the original solution was for steel. And then we wanted to look at it and say, well, what if we swapped out as much as we can with masonry and see how that affected your schedule? So this was primarily a exercise on construction schedule. So the original solution had a concrete foundation, but it had, I think the next number here, 54 columns. So that was a very complicated foundation layout for all of those 54, I should say, steel columns. And waiting on all that steel was going to take 5 to 6 weeks for the shop drawings and then the fabrication and the delivery. So what we did is we came in and, like I showed you on a few slides ago, we tried to put masonry wherever you can utilize it on the structure. So we swapped out the concrete foundations with CMU foundation, and we converted all of the 8-inch CMU to load bearing. It had a 4-inch veneer on top of that. And what we found was that by utilizing the load bearing strength of the masonry, we were able to reduce the number of steel columns to 9. So that is a huge drop in that. And then as well as coordination, the masonry could keep building and going along schedule without requiring too much lead time. So it was less than a 4-week lead time for all of the masonry. And just in the schedule savings alone on that, and again, this was a while ago, so these numbers would potentially be higher today, we found that that was a $40,000 savings. And the developer liked it so much that they decided to make that the new prototype. All right, so now I'm going to jump into lintels and a discussion on the different types that we see in masonry structures. I've already sort of given away what the conclusion is going to be, but we'll talk about a little bit more of the reasons why. So when you are looking at masonry walls, you typically see 3 design options out in the field. The first 2 definitely the most obvious. So number 1 should be masonry. If you have a masonry structure, you should be using a masonry lintel. It is the best solution both architecturally and structurally, and we'll get into those reasons in a minute. Number 2 is steel, and although we see that as the most common, at least I see it a lot, maybe the word is getting out and it's not that way anymore, but I do see it very commonly utilized, but it's generally not needed. Usually your masonry is strong enough for those lintels. When you have steel with those dissimilar materials, it creates complexity. You have to anchor it in, and you have to cover it up, and it becomes maybe more trouble than it's worth. A third option that we will also look at are precast masonry lintels. So we will start with the steel ones, since that's what we see pretty frequently out there. It is a very common solution. It is on a lot of structural drawings as a schedule or a default or a standard. But as I said, they probably should not be that common, and they definitely should not be the default. It does lead to scheduling issues because you can build your block up to the height where they are supported, but then you have to wait for your steel to come in. And steel often has a much longer lead time than block. You need corrosion protection. So anytime you put steel in there, now you're looking at flashing or treating your wall somehow. There are bearing plates that are typically required on the ends, and then those plates have to be anchored into the wall as well. In this particular picture, you see that shelf coming out to support your veneer, and that can lead to a thermal bridging issue. We heard from a few people trying to defend this practice that, well, we need to use steel because otherwise we have to shore the masonry. And although maybe it has to be shored in a few situations, there are a lot of innovative ways to avoid that. And the trade-off for putting the steel in there and eliminating the shoring is that it gets much more complicated in many other areas. So this is just one example that we see, and as you can tell from the top there, it's critical that the size of the steel lintel be considered before you just throw it into your span. The depth needs to match the coursing of the block, and then the width needs to be narrow enough to be concealed. So if you're not thinking of that off the bat, that can lead into more issues a little bit later in your construction process. If we have that plate or shelf angle there to support any veneer, now we are putting torsion or twist in our lintel. And I can tell you that a lot of engineers have not considered that either, or they just didn't know that there was going to be a support like that added later on. So if you have a steel beam, you need to consider that torsion on the beam also. Where the bearing plate lands, or where the lintel lands on the bearing plate, because of that expansion and shrinkage difference, a lot of times you want there to be some kind of movement allowed there. So in this particular example, there was a note to provide a sliding connection. But long term, if we get that water intrusion and we do get some rust, which is likely going to happen, then you no longer have that capability to slide and let those two materials move relative to each other. So once you have rust, now you have your steel contracting and pulling on that plate, and you can expect a crack to develop at the corner. The other thing that is sometimes overlooked is that at the edge of your masonry, you should have jam steel going full height. And if that hasn't been considered in advance, now it is interrupted where that steel lands at the bearing plate. Oftentimes that bearing plate, just to size it, becomes very, very large. And now you've got more steel and more steel to conceal. And again, the torsion issue, what prevents that from happening? So we have a few pictures here of things in the field. This was a bearing plate that was very large. It may be a little bit difficult to see from that angle, but then you also see that the beam has been starting, they have been starting to cover up the beam as well. This is a great picture of that crack that you expect sometimes when you see the bearing plate being pulled into the opening. Here's an example that I don't even know what to tell you. This is clearly a coursing issue, but I don't know if they didn't want to cut the block or set the block and then forgot that they needed to have a lintel bearing there. And then someone said, well, we'll just put it in anyway. And at this point, I think the door is holding up the lintel, not the lintel holding up the block. Here's a picture where we have some nice big masonry openings, and it's not a long span, but at some point it was decided that a steel lintel was needed, and those are very large steel beams. So then it looks like it trickled down and someone decided, well, now we need a steel column to support it, and now it needs to go all the way to the foundation. So there's a whole steel frame in there that could have been avoided if you just used the masonry as the lintel. So to summarize the steel lintels, it's complicated to do it right. You can see in that image there all of the different moving parts. You've got your plate, you've got bolts to bolt the plate down into the masonry, you've got U-ties to tie it back to the jam steel, which had to be moved one block inward from the opening, and just making sure that all of that gets done, it just is complicated and time-consuming and costly. So what we encourage you to do, to specify and to look for, is to utilize masonry for your lintels. So as you can see here, it matches the wall and it's economical. It's made of the materials that are already on the job site. It's fast. You're not waiting on that lead time for your steel to come along. And for door openings, typical door openings, 3-ish, 4-ish feet, masonry easily works. I cannot think of a situation where that wouldn't work unless, I don't know, you had a column that you're trying to transfer out at that lower level. So it can easily span the door opening, even easily span 6 to 10 feet. And they can be built in place on site. They could also be prefabricated on the ground and lifted into place. You could buy prefabricated lintels that are delivered to the site. There are lots of options with masonry. Longer spans are possible. They just need to be calculated or engineered. And to prove our point on that, there was a 12-foot span on a project that we worked on in Detroit. And so that was typical for that project, and we calculated it and it worked. And then another example where we just wanted to see if it could be done was a 52-foot long span. Yep, that's you're reading that correct. Now that needed to be 12 courses high. So it's not likely that it would ever be built, but again, with the right engineering and the right amount of material, it can be done. So once we switch to the masonry solution, that connection detail becomes much simpler. So now your lintel is integral with the support. All you have is the lintel horizontal steel framing in, and then you have your jam steel coming up. If it's going to be an engineered masonry lintel, then you're also going to be able to reduce some of the load on the lintel. And this is kind of the engineering part, so I don't know that you want me to get into that too much. But when you have a steel lintel coming across, it is not fixed at the ends. So you're having that beam sag and deflect, and it's what we call a pinned connection on the end. So you're looking at the full weight of the wall and the roof on that steel lintel. But if we're looking at a masonry lintel, you have some arching action. The ends of that lintel are a little more fixed, and so some of that load can actually arch or shed to the sides, and now you're not designing that lintel for the same amount of load that you are when you're looking at a steel lintel. I mentioned briefly shoring of block lintels. There are a lot of things that they can do in the field to shore those up. This is just one example. These are angles that have been put on the sides of the block adjacent to support your lintel, and then some paper put in there. And then once your lintel has developed its strength, those angles are pulled out, and then you can just repack those joints. Here are some images of a precast lintel that could be brought into place and on site, use a crane to put it up. This is a prefabricated lintel that was built on site, and then it's being lifted into place. And this is a multi-course masonry lintel that was also built on the ground and then lifted into place later. So my last section here is going to be on joints. And We're going to call them movement joints, although they are a couple of different things. We have the structural control joints, and then we have the architectural expansion. There's a lot of words that you can use for it, but there's the structural and the architectural. And generally, the structural engineer should locate their control joints, and the architect should locate your expansion joints. There is a slide here in a minute. Those do not need to align either, by the way. They can be in different locations on the veneer versus the structural masonry. So when we're looking at veneer, the non-bearing, non-load-taking part of your wall, if we're looking at vertical joints, there's a few locations where those are located to prevent cracking, if you have differential support on the wall, and those are not something that we're really ever trying to eliminate, especially not me as the engineer. I'm leaving that up to the architect. Horizontal joints, again, you may need some differential movement. Horizontal joints are never there to relieve, in other words, to keep the brick or the masonry below from supporting the brick or the masonry above. That's not why they're there. And also, in some cases, those could be eliminated. Primarily what I want to talk about are the structural joints, but just as a quick image of what I was talking about with those veneers, when you have that differential support, maybe part of your brick is supported on the foundation and part of it is supported on a shelf angle or a ledge of some kind, like in this picture. The half on the right is going all the way to the ground, and then the half on the left is supported at the roof line. Then you would want some kind of isolation or joint between those two so that that differential settlement can be accounted for. But when we're talking about structural masonry, the vertical joints have an additional purpose. They are still needed to prevent cracking, but they can also be used to isolate structural elements. And I'll show you a picture of that in just a second. It can also be eliminated in some cases. If you have enough reinforcement in the wall, you can have fewer joints, and they can also be located in different places where you may not normally see them. For horizontal joints, they have their basis in veneer, but for structural masonry, you never need a horizontal control joint. Again, the idea behind those is that someone thought that the masonry below could not support the weight above. And there is no situation where that would be of concern. The masonry is strong and it can support itself. So this is an example of a detail. You've got a beam in there, you've got some metal trying to support it. This is a picture of it trying to be constructed. It just doesn't look right. It doesn't really make any sense. So for horizontal masonry joints, then never. You never need them. I'm gonna go back to this slide in a second because they're out of order. But this is just the point I was gonna make about the control joint in the structure behind and then the expansion joint in the veneer ahead do not have to line up. They do need to be located, and where you locate them has an effect on the structure, but they don't have to align. All right, so I'm gonna go back to illustrate the point on the vertical joints. So the vertical joint can be used in structural design to direct load to or from a structural element. So this is a wall that is a quite big wall. It has some openings in it, and sort of the old-fashioned way of locating control joints in that wall would be to put them at the edges of the openings. But what you have effectively done there is you've divided up this nice strong wall into a bunch of skinny, tall panels that cannot take much load. Again, just picture trying to push something over that's tall and skinny versus square with a more uniform aspect ratio. So what we don't want is to locate control joints right at the openings. What we would like to do is move them away from openings into a more uniform location. And this is possible with the right reinforcing in the wall. And so now you just have a much stiffer, stronger wall. And it's easy to do with finite element analysis software, which is the last example that I have here. So on the top is a wall with everything acting as one, and on the bottom is that same wall with the individual piers acting. And a quick animation just shows that they deflect much much more on the lower image. Okay, So that brings us to our conclusions. Thank you for letting me cover all of that material. Number one, we want to use the available strength of our masonry or specify it higher as needed to get into current engineering and capabilities. We want to design using those current capabilities. Software, don't use tables. If you have masonry on a project, go ahead and use it, load it up. Masonry likes strength and it can take it. Don't over reinforce your partition walls, and consider masonry strength for lintels and columns. Try to review those schedules that have been carried on and either eliminate them or get new ones. So that is it for me. I think we have a few minutes for questions. Otherwise, I'll give it back over to Margie.
Any questions, anyone? No? Thank you so much, Beth. Oh, we do have one.